Okay, so we can move to the next talk by Paola FIORENTIN and Alessandro Spagna on local cosmology in the Gaia era. Are you online?
Yes, sir. Can you hear me?
Yeah, I can hear and see.
Okay, I share the screen. Can you see the screen?
Yes, very well.
Okay. I'm Alessandro Spagna, and with Paola FIORENTIN, we will present this lecture on the local cosmology in the Gaia era. Both Paola and I are members of the astrometric group in Torino, and we were involved in the Gaia mission since the very beginning. So, first of all, thanks to Professor Ruffini and to Maria Teresa Costa for the invitation to this school. I will present the first part of the lecture and Paola the second one. So, thanks to the galactic stellar population that tell us the story of the galactic formation, we can perform an interesting study of local cosmology. That's because the Milky Way is the only galaxy for which we can measure the individual properties, such as distances, velocities, chemical abundances, ages, for statistically large and complete stellar sample. One of the main stellar population of the Milky Way is the galactic disk, with a radius of about 15 kiloparsec. It includes a thin disk component and also a thick disk component formed by the very ancient stars. There is also a massive bulge in the center and a stellar halo that extends up to more than 100 kiloparsec, but contains only 0.2% of the stars of the Milky Way. As we'll see later, a large fraction of halo stars is not formed in situ, but are debris from accreted satellites and kinematically heated thick disk stars. In the halo, we also find stellar halo streams, which are produced by ongoing merging events, and also there are several tens of satellite galaxies. And then, thanks to the modern survey, we can measure and analyze details the chemokinematic properties of the ancient stellar population, in particular the thick disk and halo, which contain the imprints of the formation processes that occurred at a redshift greater than 1-2, which means more than 8-10 gigayears ago. The context is the galactic formation lambda CDM model, and the assumption of the galactic formation process can be summarized as follows. That is, the dominant mass component is called dark matter, and the density contains fluctuation with the power spectrum due to the produced during the inflation, and these fluctuations grow under the action of gravity, and the small objects are the first to collapse. And it is the cold dark matter that guides the collapse of the baryonic matter. So gas clouds form stars that form the proto-galaxy. Thus, galaxies form through merger of smaller systems. In this slide, we present the results of a cosmological high-resolution simulation of a Milky Way disk-like galaxy. The panels show the face-on and edge-on snapshots representing the gas and star distribution at various redshifts. On the left, we see the gas in fall, and we notice, you see also my cursor?
Yes.
So. You notice that a small disk of gas is already present at a redshift equal to. On the right, we see the accretion process, and in particular, for redshift before 1.5, we see a very intense accretion activity with these structures that are merging. And a more quiescent evolution at the recent time. Thus, the dark halo grow hierarchically, and smaller structures form before the larger ones, and subsequently merge into larger and larger systems. And our aim is to search for a signature of this bottom-up galactic formation in the stellar population of the Milky Way. And one of the prediction is that this model predicts a greater number of smaller galaxies, which is consistent with observation. However, the amount of expected small galaxies seems overestimated compared to the actual number of systems observed at redshift 0. And the missing satellites problem is still matter of debate. In this slide, you can see the local group dominated by Andromeda Galaxy, the Milky Way, and the Triangulum Galaxy, plus tens of smaller satellite galaxies. As far as I know, at the moment there are more than 60 known satellite galaxies of the Milky Way, including ultra-faint systems, and most of them have been discovered in the last 20 years by means of the modern digital surveys. Among the satellite galaxy of the Milky Way, I mentioned the Large and Small Magellan Cloud, as well as the Sculptor and Fornax dwarf spheroidal galaxy that we'll discuss in the next slides. Okay, and so thanks to the modern digital stellar survey, we are identifying the building blocks of the Milky Way that includes these classes, the satellite galaxies in the outer halo, tidal streams produced by ongoing merging events, stellar debris of accreted galaxy, which are scattered in the inner halo and also in the stellar disk. And thanks to this study, we can answer to questions such as how many mergers occurred in the Milky Way, when did the merger take place, how large were they, did the merger affect the evolution of the Milky Way? So these are the investigation that we and many colleagues are carrying on. And now we have a very powerful tool, which is the Gaia DR3, the third data release. As you know, just a few weeks ago, this third data release has been published. And this catalog provides positions and trigonometric parallaxes from which direct distance can be derived for 1.5 billion stars. This beautiful picture shows the distribution of all these stars. It's not a photo, it's just the distribution, where you can see clearly the galactic bulge, the interstellar extinction, the stellar disk, and the closest satellite galaxy, which are the Large Magellan Cloud and the Small Magellan Cloud. In addition, Gaia provides also, thanks to the astrometric parameters, which include the proper motion that correspond to angular velocity of the stars, for which the tangential velocity can be derived. As an example, this figure shows the stellar displacement of the closest stars within 1 kiloparsec after 400,000 years. This third data release of Gaia contains also radial velocities for almost 34 million brighter stars. Line of sight velocity combined with the celestial coordinates, proper motion, and parallaxy provides 3D position and 3D velocity. So we can map the space phase of the galaxy thanks to this data. And as an example, this plot shows the galactic distribution of the mean radial velocity in galactic coordinates of the stars in Gaia DF3. Here, light colors evidence the regions where stars are moving away, while dark colors indicate the region where stars are moving toward us. And this global velocity pattern is a signature of the galactic rotation. And for the first time, the Gaia catalog includes also a set of astrophysical parameters, such as metallicity, chemical abundances, classification, ages, and many others. And now we focus in particular on the metallicity. And metallicity M over H is an estimation of the abundance of the chemical elements heavier than hydrogen and helium that we observe in the stars. And this plot represents the medium metallicity from the general spectroscopic sample that includes about 5 million stars. Here, red colors indicate the region where stars have typical solar metallicity, or even more metal-rich, as in the inner disk here. Blue colors indicate regions where stars are metal poor, such as in the outer disk here, which are the galactic anticenter, and in the central bunch, so here. For this presentation, it is important to look also to the chemical properties of the ancient stars. And this plot shows the distribution, color-coded by metallicity, of a subset of variable stars, Lyra, which are tracers of the most ancient stellar populations. Most of these stars belong to the metal-rich bulge, which is in the center, and to the metal poor halo at high galactic latitudes, and to the thick disk. However, we also see the Magellanic clouds with the blue color, so are more metal poor. And also in green here, we see the core of the Sagittarius dwarf galaxy that is currently merging into the Milky Way. So that's an example to see how the chemical properties can help to identify populations, stars coming from other galaxies, other stellar systems. As I said, Gaia contains plenty of parameters, especially this data release, and here I reported some of them. So the total number of sources in Gaia catalog is 1.8 billion, and the sources with full astrometry is 1.4, 1.5. And I remark that the full astrometric parameters are available for this sample, which is of the order of 1% of the stars of the Milky Way, which is which is a lot. You can, and also here there are the astrophysical parameters from the spectroscopic instrument, RVS spectra. 5 million is the sample with the radial velocity, with the chemical abundances. The full list of the Gaia DFA parameters are available on the Gaia web pages. Here you can see the link. So thanks to this data, we want to derive the kinematic distribution, the kinematic information that characterize the stellar populations. A useful tool to study the kinematics is the so-called turbulent diagram that plots the galactic velocity rotation on the y-axis with respect to the quadratic sum of the other two velocity components, radial and vertical, on the y-axis. And in this plot, you see the density distribution of 60 or more than 60,000 stars within 3 kiloparsec from the sun after rejecting the metal poor stars. And these data are derived from Gaia DR2 and apogee. Metallicity in this case is not from Gaia, but from a ground-based surface. And here you see the region where the disk stars are dominating, but we also see that in spite of the metallicity selection, there are also a component of intermediate metallicity stars with halo kinematic, especially in this retrograde region with the rotation less than 0, and also in this region. So kinematics is useful, but is not enough. We need chemical abundances. And it is also important to measure chemical abundances of the individual elements because they characterize the formation processes, such as the efficiency of the star formation rate of the population. For example, the magnesium is produced by massive stars, and it is diffused in the interstellar medium by the supernova explosion, while iron can be diffused also by the so-called supernova 1A that involve less massive stars and explode on longer time scales. On the bottom, you see an example of a Gaia spectrum with the absorption line of various elements. However, take into account that ground-based spectroscopic surveys such as Apogee and Gaia, that Paola will present in the next part of the talk, provide more accurate chemical abundance than Gaia, thanks to the larger diameter of the telescopes on ground and on a more extended wavelength range. However, Gaia is also very important because it's the larger in terms of number of objects and homogeneous over all the sky as a spectroscopic. And so if we have also the individual chemical abundances, we can study the chemical evolution in time of the stellar population. And the plot that you see here has been published several years ago, so with all data. And it compares the chemical properties of the Milky Way stars with those belonging to the two satellite galaxies, the Fornax and the Sculptor dwarf galaxies, this one. The x-axis represents iron over H, that is the logarithm of the abundance ratio between iron and hydrogen. It's a good indicator of the mean metallicity. while the y-axis represents the alpha over iron, that is the logarithm of the abundance relation between a set of so-called alpha elements with respect to iron. And the alpha elements includes magnesium and other elements such as carbonium, oxygen with similar properties. So it's an average. The gray line shows the chemical evolution in time of the stellar population of the Milky Way. So first, the metal poor stars, yellow stars are formed here, the light blue dots. Then thick stars, the green ones, and finally the metal-rich young thin disk stars, the red dots. And we notice that the stars belonging to the satellite galaxy, these violet and blue, were formed through a different chemical evolution that results in a lower metallicity and a lower alpha over iron with respect to the stars of the Milky Way. And now, on the right plot, on the right panel, we see the density distribution over a large sample of stars within a few kiloparsecs from the Sun, selected with the Gaia catalog. And in this plot, the chemical abundances are from apogee, a ground-based survey, that is very accurate to measure the magnesium in particular. And thanks to this accuracy, you see that the thin and thick disk population appear now well separated, much more than in the previous plot. And in addition, you see the halo stars metal poor here, but also you can notice these elongated structures with a slope similar to the slope of the satellite galaxy. And this is the evidence that in the Milky Way there are stellar debris mixed to the in situ stars, stellar debris of past accreted satellites. And now Paola will tell you more about this. Prego, Paola.
Okay, thanks, Alessandro. So now, in order to look for the building blocks of the Milky Way, let's focus on where the signature of hierarchical merging are expected and what are the strategy of detection and characterization to find them. We have seen that according to the hierarchical structure formation model, galaxies grow by merger of dwarf galaxy. This theory predicts the presence of fossil signatures we call streams due to the accretion experienced over their lifetime. Simulation, like this one, have shown that low mass stellar system orbiting an host galaxy undergo disruptions and distortions due to the tidal forces. And this process leads to the formation merger debris with an unhomogeneous spheroidal halo-like distribution. Considerable structure is still present in the galactic halo. Indeed, in the outer halo, they remain spatially and kinematically coherent many gigayears. However, in the inner halo, where strong phase mixing takes place, merger debris are still detectable as groups of stars with coherent kinematics and metallicity, despite being of very low spatial density. This is supported by simulation, and this is what we see here on the right. This is the configuration space XZ, And this is the disruption of a satellite. You can see that after 8 gigayears, the satellite is totally disrupted, but its kinematics and motions shown in these bottom panels are extremely coherent. And the same signature is present in the kinematic distribution of a sample of about 100 giants within 1 kiloparsec from the Hipparcos catalog that in 1999 led to the discovery of the Helmi stream. Let me introduce another example with data of the pre-Gaia era. Now the local volume of the inner halo that we can explore extends up to 3 kiloparsec of the sun. However, to make the analysis and detection more efficient, we had to focus on the high velocity tail of the halo distribution. Here on the right, we have the simulation of 4 independent massive mergers having different inclinations, low, high inclination, on retrograde or prograde orbits. And here you see the final configuration in the XZ plane for each satellite. Now, shown here is the velocity distribution of those 4 satellites convolved with predicted errors for Gaia in combination with ground-based spectroscopic surveys, namely just the Gaia ISO survey. And shown are only the debris left by the 4 satellites within 3 kiloparsecs of the sun. And this can be compared to what we have on the left. We can compare to the high velocity tail of the local halo distribution from the GSC2 SDSS kinematic survey, both in velocity space, the top panels, or in the integral of motion space, given by energy and or angular momentum. Here in the bottom, the integral of motion is defined by the components of the angular momentum in and out the galaxy disk. And this is very useful as we can infer orbital properties of the progenitor. In fact, for a local sample, LXY, the y-axis is dominated by the velocity perpendicular to the plane, and which gives an indication of the inclination of the orbit, while the LZ on the x-axis measures the amount of rotation of a given stellar orbit. Essentially, stars with high, low L perpendicular are on high, low inclination orbits, while stars with negative LZ are on retrograde or prograde orbit if positive. Also, this distribution is very useful as one can discover that 2 streams are stripped from the same progenitor. In particular, associated to the Helmi streams are the fuchsia and blue streams that in the angular momentum plane are clumpy. That means they have a common origin and they run instead of near parallel orbits but crossing the Milky Way disk at high speed, one from north to sun, the other with similar speed and angle, but in the opposite direction. At that time, we identified 5 moving groups, the stars with these different colors, including, the red stars, which appear associated to a massive merger on a slightly retrograde on high inclination orbit. And this was the very first time of a few stars of the high velocity tails of Gaia Enceladus, which will be discovered by Gaia DR2 a few years later. Here we are. So when Gaia DR2 was published in 2018, taking advantage of the 700,000 stars of the RVS sample, that is with Gaia line of sight velocities, it was amazing to find and discover this. This is a tumor diagram for stars within 2.5 kiloparsec of the sun. And here, velocities of the stars in the disk are plotted with great density contours because of the large number of stars. While halo stars, which are selected with large tangential velocities, are shown as black dots. The blue dots, instead, are part of a prominent structure that was named Gaia Enceladus, with slightly retrograde mean rotation motion, selected as those having angular momentum and energy in this range. On the right, we have the distribution of star particles extracted from a simulation of the formation of a thick disk from the merger of a disk-like satellite galaxy on retrograde orbit with an inclination of about 30-60 degrees. And these are the blue symbols. And the merging occurs with a pre-existing disk, the black dots, at a mass ratio of 5:1. The similarity between the graphs suggests that the retrograde structure could be largely made up of stars from an external galaxy that merged with the Milky Way about 10 gigayears ago. Support to this hypothesis comes from the chemical abundances of stars provided by the Apogee survey. And this figure shows the chemical plane alpha over iron against metallicity for a sample of stars located within 5 kiloparsec of the sun. And still the blue circles correspond to Gaia Enceladus members. Very nicely, we see the well-known sequence of thin and thick disk stars. The vast majority of the retrograde structure stars, the blue dots, follow a well-defined separate sequence that extends from low metallicity up to high metallicity. This sequence is clear, separated from the thick disk sequence, except for the presence of thick disk stars, which are alpha rich, that have a similar phase space distribution to that of the retrograde structure. And the presence of stars with thick disk chemical properties but typical halodynamics in this suggests that some thick disk stars have been heated by the merger. Here on the bottom, we see the histogram of the metallicity distribution of the retrograde structures with or without the alpha-rich objects. And anyway, the distribution peaks at minus 1.6, and this is a reminiscent of the distribution of the stellar halo of the galaxy. But are there other massive or minor events? Are there in situ halostars? This is indeed a very active field. Here I'm showing in the energy versus angular momentum plane recently discovered halo substructures identified by several authors by means of different kinematical and dynamical techniques. Many halo substructures occupy different regions in the integral motion plane, and some also overlap. And so actually the figure was split into two panels for clarity. Also, inspection of the distribution reveals that substructures are usually investigated in the retrograde region or prograde high inclination region. But the chemical composition information is required to further disentangle the nature and reality of these claimed halo debris. This figure shows the chemical distribution, magnesium over iron against metallicity for the previous halo substructure overlaid on the Milky Way sample from Apogee and Gala. Each halo substructure occupies a specific locus. It was claimed that the inner halo of the galactic stellar halo are likely comprised of debris from three massive accretion events: Gaia Enceladus, Sagittarius dwarf galaxy, and Heracles, and a subset of less massive accretion events like Thanos and the Helmi streams. However, detailed chemical analysis, including also elements like aluminium, magnesium, sodium, may also disclose the reality of many substructures, linking them to previously known structures. And this is the case of Sequoia, Ariuna, which are associated to Gaia Enceladus, or in situ populations like Aleph or Nix. So far, we actually refer to halo substructures. However, we know that the halo permits the disk spatially, and the detection of the accreted stars in the region of the galactic disk is much more challenging, as these stars are difficult to distinguish, being dominated by in situ disk stars. So let me introduce in more detail the discovery of a stellar stream in the Milky Way disk. Certainly, a large sample of stars with accurate 6D phase space information and complete chemical properties to classify and characterize are very much needed. Such detailed information can be obtained from massive astrometric and spectroscopic survey. Gaia is providing unprecedented accurate measurements of position, parallaxes, proper motion for billions of stars across the whole sky, while the Apogee and Gala program have contributed high resolution near infrared or optical spectra, yielding precise radial velocity, good at 100 meters per second, atmospherical parameters, and chemical abundances for more than 20 chemical elements. The study started by assembling the chemokinematical survey. We selected objects with full astrometric solution without problems without any problems. We retain only stars with a distance error of 20% at most, relative error. As for the spectroscopic data, basically we rejected low signal-to-noise spectra and objects with flags warning of poor atmospherical parameters or unreliable alpha elements. So in the end, we had a sample of 400,000 stars down to the 18 magnitude, whose median uncertainty are extremely remarkable and allows to compute galactocentric velocities with median uncertainties below 0.5 kilometers per second per component. Also, orbital parameters, eccentricity, and maximum height above the plane has been computed assuming a galactic potential. So let's now introduce the selection of the halo sample. This is the chemical plane. Oh, sorry. The chemical plane magnesium over iron for the full chemokinematical catalog for the apogee and the Gaia survey separately. Clearly, the sample is dominated by tinted D stars, and we chemically identify halo stars by taking objects with metallicity less than -1, and according to the above relation, which is basically below this dashed line. Here we have the number of halo stars selected among the total. Here we show the resulting color magnitude diagram for the full sample on the left, and we do see giants and main sequence stars that very nicely appear thanks to the power of Gaia data and distances. And on the right, for the chemical selected halo sample, let me just notice that the whole stellar population is dominated by red giants. Then we focus on the local halo within 2.5 kiloparsec of the sun to limit the impact of velocity errors, and we investigate the phase space. This is the 3D velocity distribution of the selected halo sample and the 10% fastest objects. We do see clumps and overdensities of moving groups among both the full sample and the subset of the fastest. And now we want to quantify the presence of clumps. We do that by computing the two-point correlation function, which is defined here. And basically, it measures the excess of pairs of stars moving with given velocity difference above what expected from a random sample. Here we have the distribution of the two-point correlation function. Figure shows with beams of 5 kilometers per second with the 2-point for the full sample in black and the fastest stars. And there is a statistically significant signal that peaks at 10-15 kilometers per second. And this excess is noticeable, especially for the fastest objects, and indicate the presence of kinematic coherent objects, clumps and streams. We then focus on those objects highlighted by the two-point correlation function, and we assign membership to the sources in order to classify into meaningful groups these stars. We perform K-methods clustering in 3D velocity space. Let me just remind that this is an unsupervised learning algorithm we choose the data points and groups the remaining into clusters, which minimize the RMS of the distance to the center of each cluster. Here is shown the outcome of the classification with 8 groups. And the 8 groups are shown by the different colors. From the detection space, let's move to the Tumre diagram. Shown is the full chemically selected halo sample within 2.5 kiloparsec. The 10% fastest objects are in red. Members of Gaia Enceladus and the Helmi streams are shown by different symbols. And the location of known structures, Sequoia, Thamnos, Nix, are shown for comparison. This is the traditional kinematical selection of the halo. And notice that 6 of the detected streams are located in this poorly explored region. Most noticeable is the group of yellow stars that we name Icarus. It is characterized by peculiar chemical and dynamical properties that are listed here in table, with low inclination prograde orbits, which appear the closest to galactic disk. Here we have the color magnitude diagram for members of the 8 streams and Gaia Enceladus. And for reference, parsec colibri isochrones with age of 10 to 14 gigayear and low metallicity are shown. So actually, Icarus stars are old and their chemodynamical properties are clearly evidence of ancient mergers and rule out the possibility that these kinematic groups are formed by in situ stars. In order to better characterize the 6 prograde substructure, we explored the space of integrals of motion defined by the angular momentum. We compare our results to high resolution and body numerical simulation of minor mergers published by Murante et al. And used to study galaxy interaction and properties of accreted debris around the sun. In particular, in gray dots are shown debris of the 10-degree inclination prograde satellite. The consistency between the simulation and the prograde substructure is remarkable. And in particular, this figure indicates that Icarus represents the debris of a low inclination prograde satellite with a stellar mass of about 10 to the 9 solar masses, similar to the LMC. After the discovery, the chemodynamical properties of Icarus have been further investigated with the most recent data releases of Gaia, Apogee, Gala, and Jess. We further detected new candidate members, the yellow objects, and 2 new prograde streams, possibly produced by previous passages. So I think I have to stop here and we can conclude. Alessandro.
Okay.
Okay, thank you very much. And our comments or questions?
While waiting, I can remind that our colleague Maria Teresa Crosta next Monday will talk about a subject related to this. So she will present some new results about this study done a couple of years ago, where she studied the rotation curve of the galaxy and using Gaia data, and compared the classical Milky Way model, including a dark matter halo corresponding to this gray solid line, with a general relativistic model that is plotted in red. So the blue line is the Newtonian rotation dynamical model, and the red line is the relativistic model. And she found that both give a consistent comparison with the observations.
Okay, thank you very much. And if no other questions or comments, let's
may I, Carlo?
Oh, sure, yeah, sure, Jorge, yes.
Carlo. Yes, yes, thank you. Related to this subject, so specifically, it can be, may you tell us maybe how much is the improvement that the Gaia data has reached in reducing the error bars of the rotation curves in the outskirts of the galaxy?
In the outskirts, you mean beyond the 10?
Above 10 kiloparsec.
Okay. I think that Maria Teresa will be able to give you more precise answer. I can say that the new data are that she will present attain 16 kiloparsec using CFIT, because we are using CFITs, and also we are adding giant stars. As for comparison, here there is a study done by Ehlers et al. Using Gaia DR2, and she used 23,000 giant stars till 25 kiloparsec, till 20 kiloparsec. The error bars are quite small. Of course, there are also to take into account systematic errors, but she claimed that it's quite small. But regarding the relativistic model and the new analysis of Gaia DR3, Maria Teresa next Monday will tell you more.
And maybe can I ask a second question, if I can do it. I suppose you are also improving the model for the bulge and the disk. So I suppose all this comes together, right? So there are already improved models for the disk potential and the bulge potential using the new data.
Using the new data. Well, using the data, you mean the relativistic or the standard model?
The standard.
The standard. No, as far as I know, we are using known models.
Thank you.
You're welcome.
Okay, so if no other questions or comments, let's thank our speakers again. And let's move to the next speaker, Florian PEISSKER. Are you online?
Yes, I'm online.
Good. Please, let's see if the screen can be shared.
Yes, 1 second. So you should be able to see my screen.
Yes, we see very well.
And also my laser pointer. Great. So then I will start. Good morning and hello. My name is Florian PEISSKER. Thank you for the invitation. Before I will start, just a few words about myself. I work in Cologne in Germany, and so my main scientific focus is the Galactic Center region. I was working in the work group of Andreas Eckert, and now I'm in the work group of Lucas Labadie. But I will continue working on the Galactic Center, but including a little bit more a broader view also to cluster dynamics but I will come back to this later during my talk. Just a brief warning, I was asked to give a talk for 1 hour, so I have plenty of slides, but I can interrupt at some point if it takes too long. So enough introduction. What you see here is the Very Large Telescope, and I was lucky enough to travel several times to Chile in the last years to do observations with this UT4 here. And so I choose the title, The Turbulent Environment of Sagittarius A Star, which basically can mean everything, right? So I try to narrow it a little bit down, and so I'm focusing a little bit more on the star formation in the turbulent radiation field close to Sagittarius A Star, because especially in the last years, there were a lot of nice results and publications underlining that star formation is still ongoing, which is a little bit unexpected, I would say. In this talk here, I will mainly present Very Large Telescope data, but also Keck data, which recently I involved in my analysis. Below here you see some of our collaborations. I mean, at some point I have to update this list, but it's more like a placeholder to show that these analyses are not done by one person, but you have to talk to a lot of people, as you may know. So this is the Very Large Telescope again. So I was there, as I said several times, and I took this picture on a platform. I don't know if it's actually allowed to take pictures from there, but I mean, nobody said something. So as you can see here, there are 4 main larger telescopes. So this is not a telescope. So this is more like for doing weather and other observations stuff. And here are the names of them. So these can be moved, but they will not interest us in this presentation. As I said, I was there several times, and I was lucky enough to see when they installed the 4 laser guide system at UT4 here and here. So this picture I took during a test run, and for several years I was not allowed actually to show this picture, but even though, I mean, it's quite impressive, I would say, to shoot 4 lasers up into the sky and to create an artificial star, right? So the next slide will show the Keck telescope. You can see here there are just 2, right? But the advantage of using the Keck telescope is that the dish size of Keck is slightly larger. So
are attending in the meeting.
Sorry?
Only 24.
Sorry?
Who is Soro Azizi? You know?
I'm sorry?
What about your question?
Is there a question? Because could you please repeat that? Hello?
No.
Okay, good. Okay, I'm sorry. So the main
actually they are active, but not in science. They are active.
Microphone on. Please mute yourself.
Could you please mute yourself? Because I hear a lot of voices, and it's a little bit distracting. That would be pretty nice. Okay, good. So this is the Keck telescope, and the main advantage is that the dish size is slightly increased to compared to the Very Large Telescope. It's just, I mean, this is 10 meters and the Very Large Telescope is 8 meters, but at least, I mean, this is 20%, right? So you have a huge advantage, I would say, when it comes to measure precise stellar positions. So how is this actually possible? So this is the NTT, the new telescope in La Silla, and here there is a new technique involved or established, the active optics. So the active optics is actually because you have to come up with that, because if you increase the dish size to a certain level, the gravity will pull onto your dish. Especially when you move it, and then you get distortion effects, and you cannot observe anything, right? So you have these little elements here in the background that actually prevent that the dish gets distorted, and so this is the first technique that is used for these large telescopes. This is the second one, the adaptive optics, because due to the turbulence of the atmosphere, right? So there you have moving cells, turbulent cells in the atmosphere. So you have to somewhat correct for them, right? So, and for this, you use adaptive optics. And as you recall, you have seen this for lasers. So they create an artificial star, and we know, ground-based people, we know how it should look like, right? So, and then we observe this artificial star or whatever star, and with that actually we can measure the influence of the moving atmosphere, and you can see directly the advantage if you compare these two field of views here. That adaptive optics is the way to go for your observations. So now this is the galactic center region. So in my talk I will often refer to the galactic center, so I mean the inner parsec. So if you look here at the scales of this combined Spitzer image, you see here 450 parsec, which is a little bit larger than 1 parsec, right? So you see here some famous regions that are also known for star formation. But we zoom in a little bit, and again, please remind yourself to this number here. So we are now at 4 parsec times 4 parsecs. So what you see here are now ALMA observations. So that means a gas, what you see, so cooler gas, so like CO, for example, and other species. And here you can already identify some of the structures that you will see in the next slide. So this is the northern arm, this is the eastern arm, so EA and NA, and this is the western arm, of course. And these reddish regions here are the outer regions, the circumnuclear disk. So where actually people have already identified certain regions that fulfill the requirements of star formation. So just recently, so like 1 year ago, by Masato Tsuboi, for example, from Japan, he actually showed some really nice results, underlining that there are still star formation processes going on. So again, please keep in mind these numbers here, 5 parsec, 5 parsec. We're zooming in, and we're now here at the inner parsec of the galactic center. So this is the scale here, so 0.1, so that means this is roughly 1 parsec. This is again the northern arm and the eastern arm, right? And so this image here was made by a of mine, and so there here is the mini cavity. It looks like a tongue, but it's actually quite larger. So you will see later another image. So, and this image here now shows you the dust distribution, besides some stellar content, but mainly the L-band is used to trace dust, right? So cooler dust. So when I mean cooler dust, I'm roughly 200 to 800 Kelvin. So at some point, dust gets evaporated. So then it gets too hot, right? So this here, this is Iris 7, and this is a famous star. This is often used for adaptive optics, what I told you before. So, and I ranked these regions. So these regions are these regions are, or have higher interest from my point of view. So and I will go through these regions depending on how much time I will have left. So first region is the S cluster. And this where high velocity stars are found or were found. So in the 90s, 1995-ish, 6-ish, Eckert and Genzel. So Genzel, you may know this name from the Nobel Prize 2 years ago. So Eckert and Genzel, they identified in the S cluster high velocity stars. High velocity means roughly thousands of kilometers per second. And this was a little bit unexpected because people thought that, okay, so that there are like older stars there, but not that there's not so much going on there, right? And then on top of that, Andrea Gees, she actually did an analysis, so investigated the spectrum of the stars and found that these stars are young OB stars, which is another unexpected finding. And she formulated the paradox of youth. Paradox of youth means that, so we have the high tidal gravitational field of Sagittarius A star, and also the temperature. So I mentioned here the L band and the related temperatures of 200, 300 Kelvin. So, but what you need for star formation are much lower temperatures, right? So, and also some sort of non-turbulence in your environment. So this is, I mean, so this is actually the starting point of this paradox of youth. So this is the interesting thing about the S-class. I mean, there are other interesting things, but so I will come to 2. This is X7. So this is an object. So I published last year something about it, and so this is an sort of bow-shock out of 3 known bow-shock sources besides X3, which is marked here. And there is another cluster, the Iris 13 cluster, which shows some similarities to the S cluster, but so it didn't raise so much interest. So we have a lack of observations. So, and this is where the James Webb Space Telescope actually will help us because we have GTO observations coming up, and so we will be able to investigate the Iris 13 cluster in detail and compare the properties of the S cluster. And this is in particular interesting if we find matching properties for some of the matching properties, then maybe we can actually make a link here. So because this paradox of youth is still unresolved. So I mentioned this paradox of youth. So you saw this this region again. So this is the galactic center region. So I told you about this northern arm, eastern arm, western arm, and so this is again what you have seen. So this is Iris 7, this large star. This is used for adaptive optics. And if we now look at the spectrum of individual stars in the S cluster, you see here indicated by the color that mainly or a lot of younger stars are present close to Sagittarius A star, despite of course there are also older stars as expected. And so this is a highly not only turbulent environment, but also a highly turbulent field of research, I would say. So here I picked one observation of NACO, with NACO, so adaptive optics, of course, in the K-band. So this only shows now you hotter emission, right? So the K-band, so it shows you temperatures of several thousands or 10,000s of Kelvin. So dust is, we don't expect to see dust features, maybe some sort of shadows there, but not dust features. So what you see here is a lot of stars in the inner parsec, so the region that you have seen before. You can also identify already from this image that in this middle area here, like in the middle of this image, there seems to be a higher density of stars compared, for example, with this outer region here, right? And so this bright thing here is IRS-7 again that I mentioned before. So, and now I will show you something about the evolution of the telescopes. So this is here on the right. So, I mean, it's roughly the same field of view. I mean, of course, it's not exactly the same, but you see here IRS-7. There's IRS-7. Here is the so-called SMILEY. So the IRS-16 cluster. So, and as you can see here, actually. And what you already directly see is if we look at this region here, so where I'm pointing right now, so I will move the cursor away here, right? And compared with here, you directly see that there is a strong correlation with dish sizes and also advanced or new technology instruments, but also techniques like active and adaptive optics. So this is a really highly interesting stuff, and we're really looking forward to James Webb Space Telescope observations, but also upgrades to gravity at the Very Large Telescope and the Extremely Large Telescope in the next 5 to 10 years. So, and so here I zoom in a little bit to show again the region, and so there the small encircled area is shown here, right? So why are we doing this? So one part of my focus, scientific focus, is also to investigate the stellar motion of individual stars that you can see here, and it looks like that you have like roughly maybe 10 to 20 stars there, but I can promise you there are much more stars there. So, and why is that so? So when we observe a scientific target, so in space, so we have to assume that all these objects are point sources, right? So, but with the telescope itself, but also with the atmosphere, and point spread function is introduced. So you have the point source plus the point spread function, and then together you get something like this thing here, right? So this star. But you can imagine that if you have a point spread function, which can be described, for example, with an Airy ring function, then the wings of that point spread function suppress emission, right? So if you have a dominant background like this here, you can somewhat, use high-pass filters, for example, to reveal more details about the stellar content of that cluster. So in the end, you get something like between, I would say, 70 and 140, maybe even more stars that are moving around there. We are talking about K-band magnitudes between 14 and 20 max. But again, this is limited to our current telescopes and instruments. So it is expected that we find much more stars the deeper we are looking. So there are simulations out there, for example, for the extremely large telescopes that show much higher stellar content. So the question, of course, arises: why are we doing this, right? I mean, why are we looking at individual stars? So we have done this in 2020 in a publication. So we simulated, or we derived Keplerian orbits for these stars that are showing here. Unfortunately, the GIF file is a little bit short. So what it's supposed to show is that looking at this here, it shows a little bit not in random distribution or not a structure. But if we look at then, if we tilt the whole system in 3 dimensions, right, then we see actually that this whole system consists out of disks. So so one can call them disks or whatever. The main takeaway message is actually that if we are tilting the system, we are seeing that there is a non-randomized distribution of stars. So there has to be some sort of, so either initial process or external process that acts on the cluster that forms the cluster. So so I marked here some bullet points regarding the S cluster. So organized structure, I told you about this. The young age of the S cluster members. So this is an publication, or this is a plot from Habibi et al. And they showed 12 years of symphony observations where they stacked the data, right? And so, and then based on a spectroscopic analysis, they derived that these stars are really young. So young in the sense of, if we average all the brightest stars for the S cluster, we come up with around 6 million years. So connecting process. So this is a simulation of a colleague of mine, Jalali et al. So you see here the so I should have started later the simulation. You see here the scales. So it comes from the outer regions, so a molecular cloud of one species with 100 solar masses, and gets gravitational elongated by Sagittarius A star, and due to compression, stars can be formed, or star formation can be triggered. Actually, so this is an outcome of the simulation. But so for me, actually, what's more interesting is that an outcome of this simulation is that the star formation here happens, or that single groups are formed, right? So single groups of roughly 5 to 10-ish sources. So this is just an example simulation here. But so if you run the simulations over and over again, you will always get the same result, that groups of young stellar objects are formed. So and I want to talk now a little bit about traces of this process, and how to combine all this in a big description of the S cluster and what's going on in the very center. And so here I have shown an plot from a publication of mine in 2020, and so this is again the galactic center region, RS7 here, and this shows the S cluster region that I've shown you before. So here you see some of the line emitting sources, the contours, and so because you cannot see them in the continuum, right? So we have to identify Doppler shifted emission lines. Sorry, Doppler shifted emission lines, and from that actually we can trace these objects over several decades, or 2 decades. Okay, so this is most probably the source that you all know. So this is so it's supposed to be the galactic center cloud G2, and so there's an elongation here in the S cluster. So the source comes close to Sagittarius A star, gets disrupted, right? You see here the scaling, or the year, right? So after the pericenter passage, the cloud gets disrupted, and so it was believed that the flaring activity of Sagittarius A star is increased, and also it's not following a Keplerian orbit anymore, so it has some sort of in spiral motion. And so this is one perspective on this source, and I will guide you now through the process, because we had last year a publication about that, where we in detail checked the observations. So an important part for that, and so for this study, is also that we had access to a broader data baseline, right? So now Symphony is decommissioned, but so it observed between 2005 and 2019. So this is a much larger data baseline compared to this publication that you may know. So Gillis and al. In 2012 published this Nature publication, and what you see here is projected, or so what the authors did was coming from a 3-dimensional cube to a 2-dimensional representation. So the X and Y distance to Sagittarius star is here shown with an offset, and then you have here the line of sight velocity. Normally, when you have the symphony data cubes, you have 3 dimensions, right? So you have 2 spatial dimensions, right? So it's like an image, but also you have a 3rd dimension. This is the spectral information, right? So every pixel has a related spectrum. So this is then called a 3D data cube. So here this is reduced to 2 dimensions, and so this is the line of sight velocity. You see here in bluish the orbit, and here in the front there is some sort of that the authors called the head of G2, like a compact emission. So and if you ever ask yourself what this dotted box here means, is it means that every emission inside of this box here is smoothed with a Gaussian kernel. So let me explain what that means. So this outside of that box is not smoothed. Inside of the box, the emission is smoothed. So what you can also see is that there are like this structure here. It looks like it looks like one structure. It could be also 2 structures, but let's say it's one structure, but it's actually not following on an orbit, right? So which is a little bit surprising to me, I would say, because if you see an elongation from supermassive black hole, then I would expect at least it would be on the orbit. But here it is next to the orbit. So in my PhD thesis from 2018, I investigated that. So this is the orbit is due to the longer data baseline, right? And I want to underline that smoothing data is not a problem at all. But if you do it too much, you can lose actually a little bit information. So and what I have found is actually that these 2 sources here are 2 individual sources. So I can see here the so-called head, right? But so I cannot confirm that these structures here are actually, that this is like one structure. So instead, so I was tracing the so-called head or G2, right, along the orbit. So this is now a smoothed image, yeah. But the important message here is that in 2019, you recall yourself the simulation you have seen, that it's still on a Keplerian orbit, and we don't see any in spiral motion of that thing. So here it is now how it moves, right? So again, there's no indication of an in spiral motion of that object. And I think the further we are going away from Sagittarius star, I think we do not have to expect anything like that. So, and if I then look at this data cube, because it's from 2008, this data cube here, right? So in 2008, so there are just like 20 single observations. So I have the same data, and then I can see actually, okay, these structure here is, if I present this in a position velocity diagram, then actually it looks a little bit different. So again, I mentioned this in the beginning, that this is a 2-dimensional representation. This is a 3-dimensional representation. So the color here actually indicates the line of sight velocity. So this has the highest, so lower and the lowest velocity. And so we have here the position of Sagittarius star. So I think this is a little bit better in the representation. And yeah. So I talked about groups of these young objects, right? So, and then we see, for example, there's G1. So DSO is G2. I just, don't get confused. DSO is G2. So what I see here is actually, it looks like, at least temporarily, that we have some sort of groupings, right? So X8, so X8, X7, and this is there is X7.1. So the data, what does the data imply? So maybe there's some grouping, but so from these 3 sources, so we cannot see this, right? So at least temporarily, it looks like that they are like together. But we should compare this with other sources in the field of view. So here I draw in some lines showing some correlations, but I mean, of course, I'm also also aware that we have here just a limited amount of data, and so we need to investigate this more to see some sort of correlation and to make a statement if they maybe are arranged in a way comparable to the S-cluster stars. I have shown you before this simulation of all the stars. Yeah, another interesting thing is that if we now think about star formation in general, so there's this famous publication in 2012 of Sana. So, and then so stating that actually binaries alter the evolution of high massive stars, but also that most of the stars are arranged in multiplet systems. We know from this is a UCLA publication of Stefan et al. In 2016. We know from these observations or from this publication that there was in star formation epoch, roughly 6 to 7 million years ago. So in a binary fraction of roughly 70%. I know there are now a lot of numbers, but they make sense. Just wait for it. And from these two publications in 2020, 2021, see, doesn't matter. So we know that the dusty sources, so the sources that you see here, indicating a binary fraction nowadays of 7% roughly. So what you should keep in mind is that 70% roughly 6 million years ago and 7% after 6 million years, so today, right? We are now leaving the S-cluster, and this is just a rough sketch what one could do. So this is something that is in preparation, what I will show you in the next slides. So don't take it too tight and so this is just an idea and loud thinking. So cluster analysis. So we can investigate different clusters, different young clusters actually, and investigate the stellar content of these clusters. So the distinguishing thing here is the age. So between 1 million year and 2.8 million years, and so we can make a statistical analysis and investigate again the content, the stellar content. Of course, not with the Spitzer telescope observations that are showing you here, because here we see just dust, and the dust is blocking actually our view towards the towards the main sequence stars that can be seen in the K-band. So this is, I will jump over this, but this is more like this statistical analysis that I told you before. If we now look at the binary fraction, so the multiplicity fraction as an age function, right, or as a function of age, so we see actually that the youngest cluster has the highest binary fraction, and then it goes down here, right? So this is an ALMA data point. I will not explain too much here about it. So, and now the numbers that I told you before come into play. So this is the 70% by Stefan et al. In 2016, 6 million years ago, and this is the galactic center. So the S cluster actually after 6 million years ago, with the binary fraction derived by myself and Ciolo Anna. So again, this is only accounts for the S cluster, and this is more like a nice to have thing. But so this needs to be investigated in much more detail, and you shouldn't take this too serious. So this is just what I want to underline here. Okay, so this is something. So this ends the S cluster and shows you what one can do actually in the S cluster with all these sources and the implications for regions outside of the S cluster. So again, so we are coming now to the second source. So this is X7. So X7 actually is a little bit comparable to the G sources, to the sources I have shown to you before. But the main difference is that we see here a strong bow shock, right? So this is the publication of Music et al. In 2010, and so this So the observations show a strong bow shock, right? So and it was believed that this bow shock is actually created at the position of Sagittarius star. That winds are created at the position of Sagittarius star, and that these winds actually then influence X7 in a way that this bow shock is created, right? Because we see also this X7 X3 source, so there has to be some sort of linkage here. We are not sure about this at the moment. This is still part of our analysis, but or I would say fruitful analysis, because roughly in a week or so I will publish something about X3, or submit something about X3. So to get a feeling about or for this bow shock and the evolution of the bow shock and why this is interesting. So here, this is again the S cluster. So you can see also here the S cluster in 2002. There is the position of Sagittarius star. There is S2. Of course, this is an image of 2015 because, and this is the reason why S2 here is at a different position. So this brighter star. So here there is X7 shown in the Doppler shifted bracket line emission. And this is an L-band continuum. You recall that the L-band is there for dust, right? So, and here I show dust emission. So I will show you what will happen if we look at the evolution of that source. So it moves northwards, and as you can see, it gets larger and larger. I will do this again. And so here again, so you can see now it's evolving, so the shape gets longer and longer, and the question of course is, why is that so? Well, again here we have 2002, so there it's almost compactish, right? Compared to 2018, you can directly see that it's like enlarged a lot. If we now look at the bracket gamma line emission, so the Doppler shifted line emission, we see actually a velocity gradient. So whereas that the slowest part is in the front, so and then it gets faster and faster to the back of the source, right? So here's the source. And what does it mean? So it means that we are talking here about between 500 kilometers per second and 700 kilometers per second. So if we assume that this velocity gradient is caused by an speculated wind, right? So this wind must be quite powerful, and was a strong. So this is a spectrum. We see some lines here. Important lines are, for example, the iron lines, right? And the iron lines are in this sense important that we see for all the sources right off of Sagittarius star iron lines, whereas we see for no sources left of Sagittarius star iron lines. So this is also something that we, I don't know. So we see roughly 12 to 15 sources where one half is having this or showing these iron lines. From the spectroscopic analysis, photometric analysis, we actually can derive here this nice two-component blackbody fit, showing that there is a star inside, right? So this H-band data point here showing this, and that the rest is then due to the envelope of the source. And again, we can ask ourselves, why are we doing this, and what is the reason for that, and what are we doing with that? And so this is another source here. It's called X8, which is close to X7, right? And in 2006, X7 was pointing towards Sagittarius star, right? So you can see here the connecting lines. And so X8 is a much smaller source, but also shows the same behavior. So in roughly 2017, 2018, I don't know what happened there, but then suddenly X7 and also X8 are not pointing towards Sagittarius star anymore. So if we look at individual data sets over these times, these epochs, then we see actually that X7 and X8 are always pointing towards Sagittarius star, and then suddenly in 2017, 16-ish, roughly around that time, so they are not pointing towards it anymore. So this is a little bit, this raises some questions about the process, the general process, and what happens there. So one of our collaborators, Jan Klené, so we got access to L-band data, luckily. So and so this is actually no, I don't think that this is this is not L-band data. Anyhow, so we got L-band data of 1999, right? So because before NARCO was installed, they installed a prototype at La Silla, and they observed data from that. So I asked nicely if I can have access to this data, because of the high pass filter that I use, but also low pass filter that I use, I can create some access to kind of like hidden information or overshined information. So this is some output of that. So this is the comic data of 1999, and this is the earliest NARCO data. Both are showing L-band, of course, because it's the telescope that is used for the comic data is much smaller compared to the Very Large Telescope, right? So that's the reason we don't see so many details, but I identified some sources here. There must be probably S2, which is shown here close to Sagittarius star, and I identified some sources here that I marked actually. And what I see is actually when I use triangulation, I see an compact source at the position of X7, which means actually that this elongation that I have shown you before, which was not present in the data before 2000, which is, I think, highly interesting. And another outcome of this analysis is if we look at this shape and compare it with other bow shocks, it looks like that it's a little bit more compact, right? So like a tight or closed bow shock. So if you look at different bow shock types, right? So you often have this open tail, right? And here, for example, with X7, so I tilted this a little bit, so I rotated it. So I used the model of Christie, who assumed that there's a high particle density, and this density actually causes that the bow shock is closed at the tail again. So this is also part of an ongoing analysis, but there are so many interesting things, and at some point I will probably publish something about that. So that, because from that actually we can derive a particle density of the surrounding of or the immediate environment of Sagittarius A star. So okay, so I told you about the connection, I told you about the iron lines and all the other sources that I introduced now. And so when it comes to the iron lines, I told you that that we see for all these sources here that are shown here on the right, we see iron line emission, whereas for all these sources we do not see iron line emission. So I came up with this idea that that there is this, I mean, this is not an idea, this is a feature that I observed, which is actually in projection close to Sagittarius A star. So here is an Doppler shifted bracket gamma line map of that object here, right? So, and at least in projection, it looks like that it separates two areas, right? So the left area, so which is it looks like it's more shielded, right? Whereas the right area is not shielded against maybe some other origins of the wind that I was talking about. Because if we think about that this wind is if we assume that there has to be some sort of wind, right, that create these bow shock sources, then maybe it could be that the Iris 16 cluster is actually a suitable origin of that wind. Because in the early 90s, there were publications, for example, by Krabbe et al., and they investigated the stellar winds of this Iris 16 cluster. And in this sense, the S cluster may serve as an shielding region, and as soon as sources are moving outside of that shielding, they get to feel the wind and get then more elongated. So, and I think that now 45 minutes are over, and I don't want to bore you anymore with the Galactic Center, so I will skip the last last 2 points here, which are, I mean, basically the same thing as you have seen before, but with different sources. And yeah, thank you. So I see a question somewhere.
Any questions or comments?
Yes, yes, Mirabel. Yes.
Sure, please. Thanks.
What might be the origin of these thousands of kilometers of stars moving around Sagittarius A star? And the second question is whether the jet activity, past jet activity of Sagittarius A star could have triggered star formation and produce of the newly formed stars these very high velocities. What is your opinion?
So good question. So there are publications out there from Mark Morris from UCLA who suggested that in the 90s, so there's a publication, and he suggested that there were actually episodes of star formation, right? I mean, we cannot. I mean, this is a fact that we see these young stars, so they have to be brought in somewhere, or I don't know. So there are a lot of different opinions floating around. Of course, it's plausible that if there would have been some jet activity or not, right, then this could also be connected to star formation processes. But I would like to point out that the direct vicinity of Sagittarius A star is actually, I mean, it's a little bit difficult to combine this with common properties of star formation, because it is for now over 20 years known that dust features in the galactic center exceeds temperatures of roughly 200-300 Kelvin, right? So we need for star formation 10 to 20 Kelvin. So the temperature itself is really high. Then the velocity dispersion of the stars, as for example shown by Gensel in 2000, is quite high. So all these things actually hinders star formation in direct vicinity. However, I mean, we don't know. Maybe there is some mechanism that fuels the direct vicinity, right? Maybe there is some as I pointed out in the beginning with this Jalali infalling cloud scenario. So I just want to mark here, or to note that the infalling cloud scenario of Jalali is not comparable to this G2 cloud thingy, right? Because the G2 cloud was supposed to be 3 Earth masses, but when I'm talking about this cloud scenario, I talk about 100 solar masses, right? So there might be some infalling mechanism, like for example shown with Iris 13. So this is the reason why we actually investigate that region and try to see, are there young stars in Iris 13? And I mean, based on the publication so far, there are, but we would like to investigate this a little bit more in detail, right? So are there comparable properties? And if so, maybe the Iris 13 cluster may serve as a birthplace for younger stars that are brought towards Sagittarius A star or TS cluster. Yeah, again, it's a little bit hard to make here a precise statement, because there are a lot of things still need to be investigated, right? But yeah, I promise you that there will be a lot of more exciting stuff coming. Tomorrow we will have a press release actually, so I cannot tell about this, but tomorrow at the University of Cologne website you will see some of my newest publication regarding that topic. Yeah.
Thank you.
may I?
Sure.
Hi, Florian. This is Jorge.
Hi. Hi.
Thank you for the presentation. Look, so if I understand correctly, instead of looking at the problem of G2, so the issue now is that the modeling is, instead of one object, there are 3 different objects with normal Keplerian velocities, right?
Yes.
But okay, let's assume that this is the case. But
Yeah.
what we showed in our previous work is that actually, if you have because of the density gradient of the possibly because the density gradient of dark matter around the parsec, around 1 parsec distance, then you could have this kind of behavior of this reduction, this decrease of the velocity, of the radial velocity of the star. So we show that. So in particular, that would that occur for very eccentric orbits around this distance. So we are looking very much forward to this kind of objects. So we have this kind of system, which have a very eccentric orbits, showing such a kind of deviation from the purely Keplerian velocity. Can you mention something about this kind of stars?
Yeah, I mean, so in most of my publications, I'm using the Hills mechanism, right, to explain the high eccentricity of these orbits. So because it's kind of like, yeah, I don't know. It's so if you think about that most stars have formed in binary systems or multiplet systems, right? It's then plausible that also the stars and objects in the S cluster have formed in such a way. And then the Hills mechanism actually proposes that in the if there is high mass like Sagittarius a star, that it splits up the binary, so that these orbits can be or that the eccentricity can be high as for G2. So the thing is that I don't think that I mean, based on what I have seen so far from all these publications describing G2, I just want to make that clear that I cannot confirm these findings of this cloud. So this is an outcome from the data reduction and from the data analysis, and I can actually I have left out this slide, but I can rebuild this cloud actually. Yeah, so it's I can build this cloud. So I know what one has to do in order to create it. And so I strongly doubt that this cloud itself is a cloud, especially because if I use let's leave out my analysis and our analysis, but if I just use the techniques, for example, in Gillis in 2013 B or A, so there is a publication that describes how to derive the data they are showing. So I'm doing this, and the authors propose that the bracket gamma material, that the gas there is due to the this elongation and destruction of G2, right? So, but if I look in earlier years, I also see the gas there, which means that the gas was there already before G2 was there. So I think this is a false connection here that was made, and yeah. So, and on top of that, I think I told you this also in my mail like a few months ago, the data is highly noisy. Of course, I can make a threshold, right, and show that there is like a darkish background, but the background itself is highly dominating the data, right? So in order to make here preciser statements about Keplerian and non-Keplerian orbits and so on and so forth, one should look, for example, at S2, which is the brightest member, stellar member of the S cluster. So this is a source that is observed now for almost or over 30 years, right? With all the telescopes that we have at our hand, and also the best telescopes. So like gravity, for example. So this instrument which combines all 4 UTs of the Very Large Telescope with a micro arcsecond precision. So if we look at the data, if we look at the original publication, we see that they have to include NACO data in order to confirm the Schwarzschild precision. So that means actually that if we have such a dominant source in the S cluster like S2, and they still need, besides gravity, I mean, you can read it up. So this is not a secret or so. You can read up that they have to include NACO data in order to confirm that Schwarzschild precision. And that means if we for such a source that is so close to the background, I don't see that we can confirm here other orbits than maybe a Keplerian orbit.
Right. Thank you, Florian.
Yeah, but I mean, you can always, I mean, you have my email address, so just write me up, and I can, we can, yeah, I can give you some publications and send you some publications, and so yeah, I mean.
Okay. Are there other questions or comments? So, if not, let's thank our speaker again.
Thank you.
And let's have a small break. Let's try to be here at 11:45, so we can restart again the session. Thank you. See you in 10 minutes. Hello? Can you hear?
Yes. Can you hear me too?
Okay. Yes, I can hear you very, very well. And I see also the slide.
Great.
So everything is perfect. I think that we can restart the session. So next speaker is Matteo VIEL about intergalactic medium as a cosmological probe. Please.
Thank you. So thank you for the invitation. I would like to give you a flavor of the importance of the intergalactic medium to perform a cosmological analysis and to ask ourselves some fundamental questions in physics, specifically connected to dark matter, also to provide a bit of the connection with the previous talks and those that will follow in the week and the week after. So let me tell you first that what we are after is, in a way, a unique stage of structure formation. In a way, the intergalactic medium, as we will see in the next slide, will sample a period of time which nicely brackets the time that has the time between nowadays, right, redshift 0 and the redshift of last scattering surface. So it's a period of time which is not boring in terms of structural formation, in which there is the building up of galaxies, and also, you know, the formation of protocluster is really a really rich and important frontier, I would say, in the history of the cosmos, and is a frontier which has deserved in the last few years lots of efforts under the theoretical point of view and also under the observational point of view, right? On July 12th, there will be the release of the first images, scientific images of JWST, and it is expected really the high redshift universe is going to really get a boost in terms of observation, theoretical efforts, and hopefully discoveries, right? Discoveries of new physics. That's a bit the idea and the hope. So in a way, we will be here after the Dark Ages, of course, and we in between the local universe probes and the CMB. So, and of course, you know, to have a consistent history of the cosmic structure formation, the quantities that we will be measuring in the intergalactic medium has to fit a common story. I have to fulfill a common story and have to be, in a way, always to be compared with estimates of parameters in the standard cosmological model and beyond that have been recovered from the CMB or from the local universe, right? That's also a way of looking at tensions. You might have heard there are tensions in the cosmological model, and the intergalactic medium could be a possible way out to find out, whether these tensions are real or not, and whether, the intergalactic medium is able to give you a definitive answer in terms of this question. So what is the intergalactic medium? So if you need to have in mind, right, just one single slide of my talk, this is probably the most important one. What is the intergalactic medium? Basically, you have a distant source, which is typically a quasar, but could be a GRB. This source is identified through this prominent Lyman alpha emission, usually in spectroscopy. And what you see here on this side of the spectrum is the number of photons basically collected at the telescope site. And so you see that you have really a wide set of different features appearing here. This is not noise. The noise level is actually very, very small. And if you zoom in, you do find actually different lines. Some of them are narrower, some of them are wider, some of them show substructure. What is this? Well, this is just neutral hydrogen along the line of sight, and it's an atomic processes that we are witnessing here. Basically, is a scattering process between the photons that are emitted by the distant source, that travel throughout the universe, and whenever along the line of sight they meet a neutral hydrogen atom, they're typically scattered. What's happening is that there is the electron orbiting the level 1s. The electrons get kicked by this photon coming from the distant source, and the electron gets excited to the level 2p, and eventually it will get back to the level 1s, and by doing so, it will re-emit the photon that has just been absorbed in a different direction. So you hear a lot the word Lyman alpha absorption system features, but in reality, what you're really after is a scattering process. It's the Lyman alpha scattering process, and it's a very prominent and important way to observe the universe along skewers along the line of sight to a distant source. So what you see here below is a rendering of the three-dimensional cosmic web. So this is really the baryons. So I will refer to baryons as the gas in our universe. And you see that if you look at these things kind of, in 3D, it's really a plethora of structures that are appearing. There are voids, of course, there will be knots, there will be filaments. And so it's also quite important to describe topologically this cosmic web. And in recent years, there have been efforts in this direction. So let me tell you that, so the idea here is the following, that you will observe things along in 1D skewers along the line of sight, but also, and this has been a very recent finding, I would say the first papers appear in 2013, you can also probe in 3D this cosmic web by cross-correlating the information of your Lyman alpha flux in the perpendicular direction to the distant source, and not only in the longitudinal direction, not only in the direction along the source, but also in the transverse direction. By doing so, it might seem, why do you want to do this? Well, it's very important actually, because by doing so, you will be able to sample the cosmic web better and also to larger scales. Because by doing so, by cross-correlating the formation in independent line of sight, you are averaging out this so-called continuum fluctuation. This is the spectrum of the quasar, which has nothing to do with, which is not related to the intervening neutral hydrogen, but this proper of the distant source. So in a way, by doing 3D, you get rid of the astrophysics connected to this continuum fluctuation of the quasars. And these have been really instrumental for the Sloan Digital Sky Survey in the BOSS collaboration. They discovered baryonic acoustic oscillation in 3D, which has been used to measure the geometrical state of our universe at redshift 2.3, which is a very remarkable achievement, I would say. So let me stress a few things and then we will move on. Intergalactic medium is a very different environment compared to galaxies or clusters of galaxies, low density environment outside galaxies. It typically spans distances that are below the megaparsec scales up to hundreds of megaparsec scales. This absorption features produced by intervening neutral hydrogen is the main manifestation of the intergalactic medium, but of course there is much more information, right? If you look at this side of the spectrum, here these are typically produced by metal lines, and people have used those systems to infer variation of fundamental constants of nature, like the fine structure constants. Is a high redshift observable, redshift between 2 and 6, is 1D, but also 3D, right? And these have been used by several people. So when I started this business about 20 years ago, there were very few groups, but now there are more. And of course, this is very, very beautiful because, you know, we get also to review the work of each other in a scientific and critical way. And this is always good for the advancement of science. But basically, the bottom line is that these data can be used to probe constraints of dark matter. The reason being that you go to very small scales. And so I use this data to probe constraints on warm dark matter, sterile neutrinos, ultralight boson dark matter. And I will get to that soon, right, in details, in more details. The results are the following, that when people advocate these three models here to solve putative tensions of the cold dark matter paradigm at small scales, like the too big to fail, like the missing satellites, and there are also other tensions, they take these particle dark matter candidates and they measure some numbers out of this, and they claim with these numbers you will ease the tension or you will solve them, right? And this is not what we are finding. Those numbers are not those that we like from the high redshift Lyman alpha forest. So the bottom line is that if you put these numbers that are advocated to solve redshift 0 problems into the high redshift Lyman alpha forest, they will basically cause too much suppression of substructure. They will basically spoil this nice agreement that we have, and that will result in something which is not in agreement anymore with the observations. So let me tell you a very important thing first. So this does not mean that, of course, these models are ruled out, right? The nature of dark matter is, of course, something that we are after, that we want to discover by looking at this data and even other data sets. This means only that either the numbers you advocate are wrong, right, and do not fulfill the Lyman alpha forest properties, or maybe there is a redshift dependent mechanism in the dark matter field, in the dark matter fluid, that acts in such a way that the high redshift Lyman alpha forest is relatively cold, and then it gets warmer to smaller scales, to smaller redshifts, to fulfill or to ease the putative tensions, right? This is a possibility. Of course, the other possibility is that also most of the tensions can be solved by looking at baryonic astrophysics rather than at modifying the dark matter nature. I will get back to this, of course. So now we have a relatively well-established model in structure formation, which is lambda cold dark matter, is based on a cosmological constant and in cold dark matter. And we must ask ourselves whether there is room for new physics in here, right? Whether we can baptize the dark matter particle, whether the dark matter is really cold. And so we can try to tackle this issue by looking at two different things. On one side, we can look in the left side at the cosmic web as really the tracer, as a gravitational tracer of the cosmic structure formation processes. And in this respect, what people have used in the last decades is mainly the 1D and 3D power spectrum. Of course, there is much more information, but we believe that the information in the power spectrum is much more easy to interpret in a way. On the other way, there is this other line of research, which has been particularly relevant, I would say, in the last 3 or 4 years, that takes a look at the Lyman alpha forest and the intergalactic medium as a calorimeter. In a way, you look at whether your new physics can dump energy, can inject energy in the intergalactic medium and hit this IgM hub, hit it to some degree. And from this, you can infer maybe some properties on the dark matter, whether it is, you know, for example, you can have models in which the dark matter is annihilating or decaying. These models typically inject energy in the IgM, and you can measure whether the temperature evolution of the intergalactic medium that you're measuring from data is consistent or not with such a dark matter scenario. So this is in a way the holy grail of the theoretical cosmologist, right? Is the power spectrum plotted here in dimensional units as a function of scale and mass. And what you see as the blue line here is the cold dark matter. This is a purely theoretical slide, right? There is no observation here. But the point that I want to make is that this curve here will depend significantly on your cosmological model. If you change one of the 6 parameters of your cosmological model, this curve will change. If you change geometry, the BAO features that you see here will move, of course. And also at the smallest scales, depending or not whether you have world dark matter or this ADM is axion dark matter, you might have features like oscillations, you might have a cutoff or not. And so it's really the small scales that probably are the most constraining in terms of dark matter nature. And so the point that I want to make here is that this information can be used in 2 ways. You can do dynamical analysis. You can look at how much your structures have grown in the last giga years or so. And so you can look at really the growth of structure, but also by measuring the BAO here, you can look at the geometry of the universe. And then the other point that I want to make here is that you see here, there's a huge range of scales. And it's pretty reasonable that if we are gonna go for the long lever arm of the power spectrum, that's where most of the constraining power will come out, right? Because you're gonna, for example, combine observation of the power spectrum at the larger scales as probed by the CMB, observation at cluster scales as probed by galaxy clusters of galaxies, by galaxy redshift surveys. And then you can have, measurements of the power spectrum down here with the Lyman alpha forest, but also there are other small scale probes that have been used recently, like gravitational lensing, or measuring the Milky Way satellites properties, dynamical properties, or number of satellites. In that case, you will be probe things down here. And so I really believe that if it is going to be by combining different scales that you're going to make progress in the field. And it's also what is typical in this field is that different observable, right, will have, first of all, different degeneracies with astrophysics. Second of all, they will have different systematics. And it's going to be really, if you go in probe combination, that you're going to make progress in this field. Let me also tell you that before I told you that what we are observing is the Lyman alpha forest field, and you are observing a flux. A flux is a very nonlinear transformation of the density field. So flux is basically e to the minus an optical depth, and the optical depth is related to the amount of neutral hydrogen that you have in your skewers, right? And so basically the goal of the numerical cosmologists working in this field, or theoretical cosmologists, is basically to undo this relationship here, is to basically understand what is going to hidden underneath this arrow here. All the nonlinear astrophysical, fundamental physical processes, nuisances, nonlinearities that you might think of, anything that might impact your 1D and 3D Lyman alpha flux, you must ask the following question: is this going to affect my measurements of the quantity that I show here in this slide on the left side, right? So this is very important to model this relationship between flux and the Lyman alpha forest. And there are theoretical models that have been used in the past, but the most, let's say, common way to tackle the problem nowadays is through hydrodynamical simulation of structure formation. So this is theory. Now we move to data. And if you want to look at the data, this is a sample of the data that have been used for the Lyman alpha forest. Most of the data, this data, I believe all of them are public available. So you can go through the archives and you can dig them out. They are typically very ready for science, right? They're typically already processed, continuum fitted, ready to be exploited by any of you. And so this, there are 3 divisions here, because I think this is important. On the left side, you have BOSS, SDSS3, which is now DAISY, right? Has been evolved into DAISY. Until a few years ago, we relied on few 100,000 of these spectra that you see here at the signal to noise level of between 2 and 3. These data here have been used to detect baryonic acoustic oscillation, and have been used also to place tight constraints on neutrino masses of this order up to sigma confidence level upper limit. So many spectra, unfortunately poor resolution and poor signal to noise, but of course statistics will be very good. What is not going to be very good is the systematics. Then we have this sample here, which is an intermediate sample in the sense that it has a signal to noise of 30, about a factor of 10 better. But you have just 100 spectra, even though the spectra are kind of focusing at the high redshift regime, which is going to be very important. We will see later why. And these have been used to measure the thermal history in the intergalactic medium, which is the main astrophysical nuisance for dark matter measurement. And then we have this final set here of very high resolution spectra. These are being taken with Keck, the VLT, so you might have heard these names. These are typical signal to noise of hundreds, and you have typically hundreds of these spectra. And they've been used also to do lots of astrophysics, lots of galaxy formation and variation of fundamental physical constants. So this is pretty clear that these three different data sets are highly complementary in terms of resolution, signal to noise, scientific questions to be addressed, systematics involve statistical power, right? And this is good. This is very good, actually. So we saw the theory, we saw the data, and let's look at the simulations. This is the simulation, which is a way of looking at theory in a way. And what you see here is a cosmic trip, which is going to be very short through the simulations we have developed with the help of Jamie Bolton and Eval Pukvine. We ran these simulations. This is a box size of 40 megaparsec. And what you see here is really the cosmic web, right? It's a projection of the gas distribution. And I want to stress a very important point here that is basically, this is not our theoretical counterpart. And in practice, the universe is going to choose for us the directions along which, a quasar can be seen and along which you can pierce this cosmic web and investigate it quantitatively. So what does it mean in practice? It means something very good, actually. It means that basically most of the volume will be filled by large voids, regions in which they are on the blue side, right? It means that they're not very dense. While, galaxies are typically residing at the intersection of the filaments or along filaments themselves, but not in a very, large way. So basically, what I'm trying to say here is that the physics of galaxy formation is gonna have a very small cross section if you pierce randomly this cosmic web along a given line of sight, right? So it is good because it's gonna tell us that astrophysical processes produced by stars explosion, galactic winds, they are of course going to affect the Lyman alpha forest at some level, but they're not going to be the predominant effect because the cross section of the galaxies is still small. That's the most important thing that I want to convey to you, right? This cross section is going to be small, and so basically you can also compromise a bit yourself and say, okay, I'm not very much interested in modeling things down to the smallest scales in galaxies. I would like to, but I want to have the physics right in the voids. I want to get the physics right outside voids. And there maybe there is less astrophysics, for sure there is, but there will be other astrophysical aspects that of course we need to pay some attention about. So you saw this. So now you pierce through this cosmic web, and one thing that you can do is to extract the flux power spectrum, right? It's the simplest thing, is a statistical description of your field. You just do a fast Fourier transform, and it's very easy. You can do it on data, and what you get on data is these triangles that you see here, and then you do it on simulation, see whether the two kind of match each other, right? And so what you see in this plot is basically the data, and look at the residuals of the data with three different cosmological models. We have a reference cosmological model, which is this ref here, which reasonably fit the data. And then we have two models, one that has more power here at small scales, and one that has less power here at small scales. So what are these two models? This model here that goes up here is a model in which the redshift ionization has been moved by, there it was at 12, it has been placed to 9. It's been moved by 3, from 12 to 9, and then you have more power. Okay, you increase of power. And then in this other case, you have a model in which there is warmer matter instead of colder matter. So you have this model here, which goes down, less power. This model here goes up, more power. And then, of course, when you see such a thing, you should ask yourself the following question. Am I living in a universe in which there is colder matter throughout, right? Or am I living in a universe in which, for some reason, the redshift ionization is moved, right, to some reasonable number, of course, and this effect causes an increase of power because the gas will respond differently, dynamically, right, to this moving ionization, which is an important event in the gas thermal and pressure history. And this, increase of power is counteracted by a presence of warmer matter, right? I can decrease the power because there is some warmer matter present. And these two effects will cancel out at this redshift 5, right, neatly. And so if I look at redshift 5, I cannot answer the question whether I am in cold or warmer matter, because astrophysics is going to mess things up, unfortunately, for me, and so I cannot tell. So at high redshift, these are the typical questions that we're asking, right? The model ionization and the end of ionization consistently, and look at whether we can disentangle between warmer and colder matter. At low redshift, the questions are different, of course, and are more related to galactic feedback. So, for example, if you look at this is the residual. There are no data here. The residual between two flux power spectra, right? And you have an increase of power of 10% if you have galactic winds or not. Galactic winds, of course, powered by star formation and supernova explosion. And so I just want to remind the statistical error bars at redshift 2 are below the %. So if you claim that you have all the physics right, apart from the modeling of the wind, you can constrain feedback by looking at the low redshift. And so it's a different regime that I'm not going to explore further. So we do have a pretty consistent model, and I like to show also this slide here. This slide here is basically the so-called column density distribution function. It's something that is very observer friendly because the observers, they don't like to work much with flux power spectrum, but they sit on the line and they feed the lines with Gaussian profiles, or void profile, better to say, with some codes, and then they get the column density of these filaments. They get really the amount of neutral hydrogen along the line of sight corresponding to a given absorption feature. And this is what they do. And so you can do this trick, and observers do it, and they explore something that is dynamically very important. They explore something that has column density that range between 10 to the 13 up to 10 to the 21. So it's really 7-8 orders of magnitude in column densities. And if you have a model that relates these column density to densities, it's really a model that goes from voids and filaments up to the outskirts of galaxy. So it's really a model. Sorry, there is the phone. It's a model that basically probes a dynamical range which is very, very wide. It's incredibly wide, right? So I think this is important. And here is the data. And the red line is a reasonably consistent model which fits the data. It's a lambda CDA model. We don't claim that this model is fully correct because it's also rich in physics, but we claim that this is a reasonably good fit to the model. It's a bit like in galaxy formation, right? If you have a galaxy formation model right, the galaxy formation processes are somewhat so complex that if you fit with a given model, this tells that maybe you are in the correct path, but there could be other models in the wide parameter space that fit this. Sorry, there are questions? If there are questions, please interrupt me at any time. Let me Yes. So let's go back to fundamental physical questions, right? Dark matter. We change the nature of dark matter. We put it warm. What does it mean, put it warm? We allow for a free streaming scale of the dark matter. The free streaming scale, in this case, is thermal dark matter relic, is related to the mass of the warm dark matter and the amount of dark matter. And we run the same simulations, in one case with lambda cold dark matter, in the other case with warm dark matter, and not surprisingly, maybe, this free streaming scale can be seen as an effective pressure of your fluid component, which erases structure at small scales. And so in such a way, it's possible, right, to really appreciate even by eye the striking difference between the cosmic web down to the smallest scales. And the higher the redshift, actually, the stronger this difference between lambda cold dark matter cosmic web and warm dark matter cosmic web is, right? And the reason being that you are closer to the linear theory at high redshift, and in the linear theory, the free streaming scale is more prominent, causing a cutoff in the power spectrum is more prominent. After that, nonlinear evolution of structure formation will work pretty much in the similar way in the two universes. And so basically it will start to destroy, to eat up primordial information and to make it more similar in the two cases. So the higher the redshift, probably the closer you will be to the linear behavior, and the closer you will be to measure maybe a free streaming scale or a cutoff in the power spectrum in your observable. So unfortunately, this is not this cutoff is not the only scale that causes a suppression of power. There are other scales that are causing a suppression of power. For example, the thermal scale. Your intergalactic medium has a temperature, and this temperature means that your lines will be Doppler broadened, right, by the temperature, and this will cause a 1D smoothing of structure and suppression of structure. Then there are also two scales that are related. The gene scale is related to pressure, and related to the gene scale, there is a so-called filtering scale, which depends on the previous thermal history, which takes into account the hydrodynamic response, that means the pressure of the gas, to the thermal history. So the pressure scale is somewhat integrated, if you wish. The thermal, and it is 3D. The thermal scale is instead 1D and is related to the temperature at that given redshift. Of course, these cutoffs are also somehow comparable, at least if you look at this course, with the warm dark matter cutoff. So for example, if you just have one number that measures the suppression of power at small scales, at a given scale, this is expressed in kilometers per second, but megaparsec over h will be a factor this number divided by 100 roughly. So this 90 kilometers per second corresponds roughly to 1 megaparsec. You see the evolution of these three different scales, astrophysical scales with redshift, and the evolution of the corresponding or similar in spirit, but not quantitatively, warm dark matter cutoff. What does it mean here? It means something very important, that there is a redshift evolution for the astrophysical scales, which is very radically different from the evolution of the free streaming scale of the dark matter. And this is gonna answer a very important question, and it's related to what I showed in the beginning. If you just take one redshift beam, you can always find an astrophysical model that fits equally well your data, whether you have warm dark matter or cold dark matter. Yeah, you just adjust the scales and you change the suppression of power and you fit the data. But if instead you look at things in a wider perspective by opening up the redshift range, things do change. And the astrophysics evolution is going to be different from the astrophysics of fundamental physics, from the physics of fundamental physics. And so that means that really we are able to break the degeneracy between astro and fundamental physics by looking at the different redshift, at wide redshift ranges. And of course, you can also, right, make jumps and make the astrophysics, you know, to mimic perfectly at each redshift beam your data. But that will result finally in a very contrived evolution of the astrophysical setup, which is something that somewhat is not very much needed under the physical point of view. The status about 10 years ago was the following, that you see here you have the data low resolution data, high resolution data, are actually between 2.2 and 5.4. And the green line is the best fit lambda cold dark matter model. The world dark matter is this red dash line. And you see that it starts to fall short, especially by looking at these high resolution small scale data sets, right? While at low resolution, the effects of world dark matter is somewhat minimal. So 10 years ago, we got this number, which is around 3 keV for this thermal world dark matter. So the mass has to be larger than that. If it is smaller, then there will be too much free streaming, too much pressure, too much erasing of a structure at small scales, and thereby drop of power at these small scales here. So it's a remarkable test of cold dark matter structure formation in an untested regime. Here, there are, of course, galaxies around, but not that many. Here, we are not using galaxies. We are not using clusters of galaxies. We are using initial conditions that are fixed by the CMB, evolve them further down to redshift 2.2, and see whether or not what we get, whether or not is in agreement with data. And it is, right? And so it is a test that could have failed, but impressively, it didn't fail. And I'm very proud of these results. So about 3 years ago, we checked these numbers with also these 3 different data sets, right? This is called, sorry, 2 different, is Q100, IRIS, and Mike. And this is the posteriors of 1 over the mass. We use this variable because in such a way, in the MCMC, we are performing this is basically, this number is basically bound at 0, right? Because if the mass becomes infinite, it means that you are in lambda cold dark matter case. And you see here that the blue is somewhat here. The blue is this XQ100. And when you add this IRIS and Mike, which has better resolution, you go down to the green case, right? So it's really by having, you know, the 2 observables analyzed together in combination, in probe combination, that you squeeze your posterior in a parameter space that is very reasonably in agreement with 1 over m equals 0. So very reasonably in agreement with lambda CDM, of course, with an error bar, right? This is the 2 sigma upper limit. And for the 2 sigma upper limit, the likelihood, you integrate this likelihood till it gets to the 95% level, it's going to be just going to return numbers that are in this case something like 1, 2 kV-ish. In this case, is probably 3 kV-ish. And if you have this, it's going to be 4 and 5 kV, something like this. So you do such an exercise. If you do such an exercise, is really you get is doable by the fact that you are analyzing a consistent thermal history, which is smoothly varying, right? What you see here is what you gain when you assume that the thermal history of the intergalactic medium evolves smoothly. So basically, if you have just this is Q100, you are here with the blue or probably violet area. Sorry, I'm partly colorblind, so I cannot recognize this. If you use only the high redshift, is the red here. When you consider the 2 together, you have the underneath green band, right? You ask yourself that they evolve smoothly, and if you do such a thing, you fix the thermal history, and then your world dark matter constraints gets much better, right? But of course, you might want, and it's perfectly a perfect attitude in a way. You say, no, I don't trust this. I don't want the thermal history to evolve smoothly. After all, we know that there could be some events in the thermal history that they can shake things up, right, and mix things a bit. And so you can also ask the temperature to evolve in beams. So we are less conservative. Sorry, we are more conservative. We have more parameters. And if you do such a thing, you go back to the 3.5, 3 kV number that I was quoting about results of 10 years ago. But if instead you ask the things to evolve smoothly, then you get 5 kV, which is a very important number. Let me also tell you that recently people working in strong lensing, they started to analyze these things with the different observable, of course, and they get numbers that are even larger than this. They get 5, 6, 7, 8, even 10 kV in some papers. So I'm a bit skeptical because maybe because I don't know the field very well, but the line alpha is not the only observable that is going to put pressure on what that has put pressure on these world dark matter models. there are also other observables that are putting a pressure to a similar degree compared to the intergalactic medium, and they are in good agreement, of course, with the Lyman alpha forest. So what we do now, what are the frontiers? So far it must seem that there is no astrophysics whatsoever, but in reality there is, right? One thing that we are after is that since these high redshift Lyman alpha forest data are so interesting for us, we want to focus on those. And what people have noticed is that there could be some leftovers organization, even at redshift 5, 5.5, which results in islands of neutral hydrogen, which could be as large as hundreds of megaparsec. And these have been modeled with semi-analytical models by Kulkarni et al., by Laura Keating and other people. But this is an effect that we didn't have in our simulations. And so we might want to ask whether if we put this effect in the simulation, we get the similar results, right? And so basically we did radiative transfer, we put these effects, and it's going to be complicated, right? Because this astrophysical radiative transfer is kind of time consuming. But what we have, some new features that we have is some, you see the comparison with the simulation that we had before, is that we have some leftovers of heated up gas that were not present in the original simulation. See here, the gas is hotter in this void. And a few years ago, we didn't have such an effect, but now we have this heating up of the gas, which is due to the fact that the reionization happened recently. This was also supposed to be a movie, which basically follow the reionization process, also in terms of not only in temperature, but also in terms of pressure. Really follow, right? This is blurred. The blurring that you see here in this image is a physical blurring. It's the pressure of the gas. It's not poor resolution on the screen. It's an effect that is physical, and we know. And we might wonder whether, you know, this pressurized gas is in agreement with the data. And so what we get is the following: that if we allow for such an effect to happen, then the flux power spectrum will get boosted at large scale and will get suppressed at small scales. So ideally, if we had to resurrect war dark matter, we would have wanted something of, you know, opposite trend here, something which resulted in an increase of power at small scale in such a way that it could counteract the war dark matter effect, right? In practice, we get something which is mild, but goes in the opposite direction. And this has been obtained also by several different groups, not only by us, with very different codes and with the very different techniques, and by people also not very much interested in the dark matter. So I am tempted to say that probably you are in the right, this is a physically motivated correct answer, which results in a decrease of power at small scales that does not impact on the dark matter constraints. So I believe I'm running out of time. I've been quite pedagogical. Let me sketch through some slides that kind of want to, you know, give you a bit of an idea of the kind of research that is made at this very moment. So in this case, we have here an interaction between dark radiation and dark matter, which is modeled in such a way with a cross section and with the time evolution. This parameter psi basically parameterize the amount of dark radiation with respect to standard radiation. And what I want you to understand is that depending on the setup of these parameters, you have cutoffs here at small scales, but also you have features, you have oscillation at small scales, and you might, that are physically motivated, right? And you might want to ask yourself whether this is something that you just 5 minutes left. Perfect. Yes. That's something you can measure from the data. Then the other thing is we do measure this from the data, especially in combination Lyman alpha with the CMB. You do measure psi, which is the amount of dark radiation, and the strength of the interaction. We will put bounds on these two quantities using two observables that are very complementary, right? And we are in this range of the parameter space. More recently, we looked also at dark matter baryons interaction. You might want to ask yourself whether dark matter is interacting with baryon with a given cross-section. And in this case, look at the posterior. We do find a very weak, of course, not statistically significant evidence that there is such an effect. The dark matter baryon can interact. The Lyman alpha forest support this with a given cross-section. And for a given fraction of the dark matter, interactive dark matter baryon. So basically, we open up this parameter space by looking at more contrived, if you wish, but physically motivated dark matter models that are able to modify the power spectrum. We ingest this in the hydrodynamical simulations, we let them run, and we compare the flux power spectrum with the data. And we see we get posteriors on fraction of dark matter. This sigma is the cross-section with the baryons. This NF is a parameter that parameterizes the slope of the linear matter power spectrum at small scales. We also look at the scalar dark matter. The physics is here, is very important, is very interesting. It produces all this setup of granularity at small scales. Let me finish in a couple of slides or so. And so we checked for that. Not surprisingly, also in this case, we do find numbers that are not very much in agreement with the claim numbers of 10 to the minus 22. We want something which is at least 10 times larger than this. We are not very much supporting a scenario in which these ultralight axons are of the order 10 to the minus 22 because it would cause too much of suppression of structure at small scales. One thing that I want to conclude is basically is this thing of the calorimeter, right? So now we look at the low Redshift Lyman alpha forest. One thing that you can do is basically you can fit the lines with Gaussian profiles. The width of the Gaussian is this B parameter, and you can ask yourself whether the lines are broadened in such a way that they fit the theoretical models, which is simulations. So what you have here is that these are real data, the points, and you have a set of different models that passes not through the data points. One model passes through the data points reasonably well, which is this dotted model, in which you artificially heat up significantly the cosmic web in an unphysical way to make especially those data points here fall through the theoretical model. You see, in this case, you do. These are models that are based on AGN feedback. Illustri, Sherwood, you might have heard these names. They're very popular among the galaxy formation people. They don't fit the data. So now we have a model, which is this so-called dark photon dark matter, in which basically the Lagrangian, the standard Lagrangian of electromagnetism is modified in such a way to allow for a new particle, which is described by a mass and an epsilon term, which describes the kinetic mixing with normal photons, with the photons that we know of. So basically this particle at some point will start interacting with the normal photons and emit radiation, emit photons in the universe. And it will do such a thing in a redshift dependent way, right? It will happen at some redshift depending on these two parameters. The epsilon will cause a different heating depending on the epsilon value. And also, most importantly for us, this kind of, release of energy into the intergalactic medium is a density dependent way. And so the thermal history of intergalactic medium gets heated up at different redshift depending on the different density that you're looking at. It's a very interesting candidate because it's incredibly simple, right? This Lagrangian for particle physics is incredibly simple. It's not very much motivated by any anomaly, I would say. Let me state this first. But it can explain the fact that we do have, at such low redshift, some anomalous amount of heating that we cannot explain through astrophysics. And so this is the parameter space that we are constraining, epsilon and m. The mass of the dark photon is about 10 to the minus 14. The epsilon is about 10 to the minus 15. And we do have this 1 sigma and 2 sigma contours for such a particular model. These are my conclusions. Lyman alpha forest is a robust cosmological probe. Is a parameter that constrains several non-cold dark matter scenarios. This is a school, so I tried to be pedagogical and I went very fast through the results. But the bottom line is that any feature appearing in the linear matter power spectrum can basically be quantified with a comparison performed in the Monte Carlo Markov chain Bayesian statistics with the data that are publicly available. So far, we do not find any evidence, statistically significant evidence for new physics beyond lambda cold dark matter, even if there are hints that there could be some promising paths through of new physics, right? And especially in the last slide, I show you the usage, which is relatively new, of the laminar alpha forest as a calorimeter in such a way the advancement in the measurements of the thermal history in the last few years has been so remarkable that you can really quantify how much energy is dumped at any given ratio between 0 and 6, I would say, in your IgM. And you can say whether there is some dark matter able to heat the gas up. You can heavily constrain, significantly constrain this dark matter candidate. Thank you. I stop here and thank you for your attention.
Thank you. And so there are questions or comments?
May I ask, Carlo?
Yes, sure.
Okay, yes, so to Matteo, that you mentioned about the ultralight actions, but what about the light actions of order of milli-electron volts? Can you mention something about them, please?
No, yes, that's a good question. Those for us are behaving like cold dark matter. So they're perfectly in agreement with the laminar alpha forest. And we don't have the discriminating power to sample those scales, the scales at which, you know, maybe a cutoff or some features in the power spectrum will appear. So for example, even if there is, I don't know, supersymmetric dark matter, like, I don't know, neutralino, gravitino, at very small scale, you do expect a cutoff in the power spectrum, but this will happen at the parsec scale, probably for such a candidate, and we cannot reach those scales with these observables. You need to look at something else. I suspect that for the action that you're talking about, the QCD action for sure for us is like cold dark matter. 10 milli-electron volt action is probably even more the case for this. What we are really sensitive to is this 10 to the minus 22 electron volt action. In this case, we are sensitive because there is a cutoff in the power spectrum at the scales that are probably by the laminar alpha forest. And we're also sensitive to this actually action here that you see in this, to this particle, to this boson here, right? This dark photon is a boson, because we are sensitive in the laminar alpha forest because through the energy that this particle is dumping into the cosmic web. Okay, not through the cutoff. If you look at the power spectrum of this candidate, it will be lambda cold dark matter, basically. Yeah.
Thank you.
Can I ask a question too?
Sure. Yes, Rafael.
Yes, hi. So I see that you have some certain preference for weak evidence, as you mentioned it, for dark matter interacting with baryons. Which sort of features are preferred in these models? Some sort of suppression at a given scale, some sort of bump in the initial power spectrum. What sort of features do these observables prefer?
That is an excellent question. And the bottom line is that we are sensitive to do two things mainly. One thing is that really, you see this NF here, for example, NF is really the curvature of the linear power spectrum at the scales brought by the forest. So it's not it's something at a relatively small scale, I would say scales of the order of few megaparsec. And it seems that the data that we have are kind of, they suggest a slightly different shape compared to extrapolation of lambda cold dark matter. So the first answer to the question will be a shape. The shape is a bit different, and you see this likely here is kind of, you know, at the preference at the peak of the cross section is a slope which is slightly more negative. So it is slightly steeper than the slope that would have been suggested by, let's say, lambda cold dark matter. Okay. So is the slope. But there are also some other papers by people probably who also working on 21 centimeter, things like this, that they look instead at the oscillation at small scales. And I believe that's a very important new kind of area of research, because if you will be probing, you know, bumps in the power spectrum small scale oscillation, this is more distinctive than the fact that we see here. It's much more, in a way, easy to see, easy to spot in the data, provided you find the right observable tool. Yeah.
Okay, perfect. Thank you very much.
Thank you, Rafael.
Are there questions? or comments? So if not, I think we can thank our speaker again.
Thank you.
And thank all the speakers of this session. I think the session is over now. There are no more speakers on my list. And so thanks to all the speakers and to all who joined the discussion and who listened to talks. And see you tomorrow for the next session. Goodbye.